The quarter wave aerial I fitted to my boat works extremely well. You can just make out the line of the counterpoises, which is copper tape which has been painted over on the coach roof, and for 17.5 inches height it works very well. I haven't got a VHF analyzer, but the computer model shows it to be pretty good, and judging by reception and transmission reports, I'm extremely pleased. It seems to work extremely well for a very little outlay. Well, here we're back in my workshop. There's one guy on YouTube that's shown how to make a quarter wave marine band aerial, but he doesn't show, he shows no matching, no counterpoise, loading of any description. So I'd like, well, not necessarily to prove that he's wrong, but more to prove I'm right. Okay, this piece of tin, which is all I've got, isn't really big enough, but this represents my counterpoise, the reaction to the driven element. Careful. With a quarter wave we have high current at the base and no current at this end. There's nothing at this end, but because current and voltage lag in a sinusoidal wave, conversely we have very high voltage at this end and none at this end, because this is at earth potential. I can demonstrate that we have high current and the current decreases as we go all the way up, and I could, except I'm averse to pain, show we have high voltage at the top and it decreases as we go down at any given time. So I've given this sort of talk at a local club many years ago, and a lot of students, while they accept what you say, it's hard for them to grasp that actual current does flow at this point. This has been a bugbear about cable feed links with the CB fraternity for years and years. Anyway, I'm not going to go there, So this represents our ground plane. It's all I've got, but it ideally wants to be bigger. So this represents the radials I put out on my top of my coach roof. And to show that there are current here, I've connected this socket up to my transceiver, and I've made, very carefully, a festoon bulb on the end of a piece of rod, carefully soldered that on, and I've soldered a festoon bulb on the other end. And to show that I'm not cheating, it's a bit delicate, so bear with me. To show that I'm not cheating, I've got a power supply there. We'll switch that on, providing I don't break anything. If I put the meter here, that bulb lights up. Get my hands out of the way. That bulb lights up. And if I come to this end, that bulb also lights up. So there's no trickery going on. Switch that off. If I put it in here without breaking the... Yeah, that'll do. What I would like to have done is had festoon bulbs all the way up, but I'm not that good. I would have done it at one time. What I need is a laboratory assistant, guys. Any volunteers? What do you mean you're not coming that far? Okay, so here's my, this isn't marine band, this is 2 meters, but it's pretty close frequency wise. So here, if I key up, first of all I've got to switch on. If I key up, you'll see the bulb glows at the bottom, because this is where our highest current is. And this is where our high voltage is. Believe me! If I think that categorically proves that we have a standing wave of current at the feed point of a quarter wave. Can't be any arguments now. Okay, so does this principle apply to all frequencies? Well, yes, it does. To give an idea of scale, here's a 1p coin, and a festoon bowl just stood up on end on the socket. This represents a quarter wave at 70 centimetres. I'm afraid I've sold my 70 centimetres transceiver. It's very quiet around these parts on 77, so I sold it. And but if I hadn't sold it, I could have shown that the bottom half or quarter of the filament glows and gradually gets dimmer as you get towards the top. The principle is exactly the same, and that very same principle is the same with the aerial in your mobile phone. That's something for you to think about.